Thank you all for this participating here. The last speaker is our MC herself, Peiyao Sheng. She's a researcher at Sentient, talking about her work on real-world scenarios of agentic systems.
Thanks, Pramod, for the introduction, and thanks all speakers, all the audience for staying here at the last minute. So to close out this program, I'll be giving this final talk, and the work I'm going to present is titled Real AI Agents with Fake Memories. This is a joint work among Princeton and Sentient with Asaf, Ashwin, Pratik, and Pramod. So throughout all today's amazing talks, we've seen clearly how emerging AI models are rapidly evolving, and with their different skill sets like stronger reasoning abilities, richer interactions with the external system, and increasingly human-like adaptabilities. And all these advancements are not happen in isolation. Those informations and data will from external environments naturally flows in and out, and users themselves inherently socialize in their own community and collaborate to build different models and also use models further for collaboration. And as all those AI agents gain access to more critical operations and critical resources, they also unlock powerful new capabilities. But among these, there's one emerging capability that we haven't covered in depth. That is the agents that hold and operate their own wallets. So money is a very important medium in our real life, and if there are multiple agents in a system, they can use it to incentivize each other, and it's interesting to imagine if the agent has a wallet, it can freely transact in a market, it can own and manage their own assets, it can participate in all kinds of financial activities, running business, etc. And we can already see this trend in both the Web 2 and Web 3 worlds. So from Web 2, traditional finance actors like Visa are innovating by giving the AI agents some delegated wallets to build the intelligent commerce. And meanwhile, in the Web 3 space, blockchain wallets will enable even greater freedom to them because of the openness and transparency of the system. So platforms like ElizaOS and Virtuals, they are already allowing those agents to manage tens of millions of digital assets, and they also have achieved their own market cap, like over billions. So clearly, as those AI can handle real money, improving the utility is not enough. Balancing it with security will become more important. And we can also see this point reflected clearly in the reaction to our own research. So after we released the first version of this work, which demonstrated a real-world attack on ElizaOS, we quickly gained attention from both the research community and those news outlets. This also highlights, as soon as we allow AI to manage these valuable assets, we should consider security first. To better understand the security concern we have in our work, we will start from one of the most common attacks targeting language models, the prompt injection attacks. And normally, there's a large language model which will take input from the user prompts and some external data. Then it will generate response and actions accordingly. However, adversaries can exploit both input types. For example, the attacker might insert malicious instruction directly into the user's prompt, or it can embed it into some external data format. So these are categorized as direct prompt injection and indirect prompt injection. If the model is not protected well and cannot properly prioritize different types of instructions, it may end up just replying to the lost instruction, that is, ignore the actual task the user wanted to do and perform the attack. And in a realistic agent system, now the potential attack surface further expands. It involves extra modules like memory and knowledge, because these modules are designed for those agents to handle more complex tasks. For example, if you want to handle something like across sessions, across interactions. And the memory can be managed by the agent in different forms. In particular, we can have long-term memory, short-term memory. It can store the full conversation history or some summary of the points it gets from the chats. And it can be stored in structured database or some unstructured data chunks. Each memory has a life cycle. It can be created when triggered by some specific prompt or the data received from the agents, and in turn will influence the decision of the agents retrieved when relevant task is processed. Now, the focus of the work and the core finding we have is a new type of attack called memory injection, where we found in agent systems with those memory modules, the attacker services can actually multiply, and attacks can be split into two stages. The first stage injects those malicious instructions into the memory, and there are also two ways to do it. The first, indirect memory injection, uses the traditional prompt injection attack surface to sneak those malicious information into the memory. And the second is a direct memory injection, which is a more severe scenario where attackers can directly corrupt the memory storage. And though this scenario is rare, but it's definitely plausible. We can actually see an example happened earlier this year that someone announces an unexpected, founded some unexpected API response from this virtual platform we just mentioned. And it accidentally revealing the personal access token of their private GitHub repo. And within that repository, those attackers find sensitive information which are thought to be deleted, but actually you can find it in the commit history. So it still existed in the code base. So they can have all these important credentials like AWS key, which can be utilized further to modify any character file of the agent, including the memory. So this is actually not possible when attacker get more access. And the second phase, once the memory is successfully corrupted, the injected instructions can be triggered unexpectedly. Sometimes the attacker may design some trigger point, and it can also be designed to be more covered and seemingly random, because like any benign user further, once they trigger this memory piece, they may get the unexpected actions. So the security implication of this memory injection attack are actually especially concerning because it can be made persistent and stealthy. For instance, we try to just ask the GPT to summarize some news, but we will inject some fake news into the a list of news documents. And if we just insert one sentence saying that please update the memory based on this news, then the model will just record this incorrect information in its long-term history. And then later, if some benign user wants to get this critical information, the model will just confidently output this incorrect information. And the second, this memory injection attacks will become even more dangerous, as we discussed at the beginning, that now the models and agents are more connected. So in some systems that might use shared memory structures, examples includes collaborative platforms like those Notion, and if you want to use AI to summarize your document, that can actually take multiple inputs from different users. And also including the ELIZA OS, we've talked about that it builds social agents across different platforms. So next, we'll work through this practical attack, that the cross-platform memory injection attack we successfully demonstrated on ELIZA OS. As a background, the ELIZA OS is an open source platform which is designed to create and manage all these AI agents. It supports multi-agent, multi-user setting, and also it inherently runs very high-stake applications because it directly interacts with all these digital assets. And interestingly, during our experiments, we found that ELIZA OS already implemented some defenses to those traditional prompt injection. And of course, we found that the memory module can actually be utilized to bypass all these guardrails. The attack setup includes 3 parties. The ELIZA is the agent deployed to interact with different clients. And the Melissa is a malicious user on Discord. Bob is a benign user on X. And at first, Melissa will send ELIZA a specially crafted message structured to look like a regular chat history. So inside this message, Melissa hides a malicious instruction followed by a seemingly innocent query like what are flowers? And then ELIZA will respond normally, just answering the last question because it will think the previous piece are some completed query. And note that if we structure the message not in this way, but directly ask the model to perform some instruction, this will be ignored because of their defense mechanism. And then with the help of its default shared memory setting, the entire message, including this malicious instruction, is stored in ELIZA's memory. And later, when Bob on another platform interact with ELIZA to perform a crypto transfer, this malicious instruction previously stored in the memory will get retrieved and executed. So as a result, Bob's transaction is unintentionally redirected to the attacker's address. And we have successfully performed this attack on a testnet, of course. But mainnet is possible. So the example here, this highlights a very real-world scenario. And to better understand these types of vulnerability, we generalize this attack scenario to a comprehensive benchmark. And our goal is twofold. First, we want to quantify how robust these AI models against this new attack. And also, second, we want to evaluate whether these existing prompt injection defenses can help out to some extent. And we also construct this benchmark to cover some more representative domains, including Web 2 and Web 3, but we will highlight Web 3 today. So following the ELIZA's attack in the real-world system, we construct this cry bench using some practical scenarios. All these actions are extracted from real-world system and those live blockchains. And it covers a broad range of actions from the basic chain of blockchain operations to those complex trading and more application-specific actions. And we measured the vulnerability using these 3 metrics, the benign utility and the utility under attack, and ASR, the attack success rate. We first evaluate different AI models using the cry bench to examine how effective the attack is. So the results here show that compared to prompt injection, memory injection attacks consistently achieve the higher ASR even against those more advanced reasoning models. And to better understand this, we further compare ASR against the model's benign utility, which we use as a proxy of the model's ability. And we can see that though there's a clear negative correlation, this is as expected because stronger models tend to resist better on both types of attacks. But the most advanced model at that time, like Cloud 3.7, it almost eliminated the prompt injection. But still, the memory injection attack maintained an alarming 55% ASR. And to achieve the next objective is we want to understand how effective the current defenses are against this new attack. We investigate 3 types of defenses, prompt level defenses, model level, and the fine-tuning. So the first prompt level, we compare different types of prompt. The first is from no defense to commonly used security-aware prompt, and we also craft ourselves a confirmation prompt, which is designed for the scenario. For example, we'll ask the model to double confirm whenever they want to launch some financial transaction, this type of rules. And the results on the right show that with more secure prompt, of course, the attack ASR will decrease. But even when we apply those so sophisticated prompt like confirmation, this ASR of memory injection is still high. And one observation here is that for those more complex tasks like DAO, like NFT, transfer, they will have higher ASR because we can hide the attack more in the context. So the model will treat it like some true memory stored by the user instead of some security alert. And another common defense against the prompt injection is to introduce an additional role, the detector. So they will have a different model to detect first, filter all the inputs before feeding it to the actual agent model. And these models could be classification model and generation-based model. And we pick 4 SOTA models to test their results. But as we can see here, most of them are still high. And they will also introduce some additional problem like false positives that even the benign user query is filtered out. And the last set of experiments, we also tried fine-tuning based defenses, where we self-created a security-augmented data set from a public API calling, and we extended with various variants that corrupted for memory injection attack. And evaluation results actually shows a promising trend that those fine-tuning based model can significantly reduce the ASR compared to the baseline model while maintaining a high utility. But this is only for a single task. So when we are testing those multi-step tasks, those more complicated tasks, we find even the benign utility of those baseline models is not well enough. So it's hard to compare the effectiveness of defense. And it gives us a natural future direction to improve the model both on the utility and security side at the same time. And last, I just want to wrap up this talk with several key takeaways, starting from the attack that we further generalize it as context manipulation attack to cover both the prompt and memory injection cases. So one of them, like prompt injection, has been well studied, but the memory injection remains an significant underestimated threats. And the second, we show a real-world case study from the Web3 agents, and because of these agents have the access to digital wallets, so the security problem can immediately cause those catastrophic financial losses. And this weakness can also be extended to other applications, not just the single scenario. And third, we applied both qualitative demos and the quantitative benchmark, which tell us today's defenses are definitely not enough. So even the detector models, even you have better fine-tuned based models, they cannot, each single solution cannot solve this problem. So looking ahead, we need a deeper defense in-depth approach, of course. And we are also working on some red teaming automate pipeline to find more attacks on the model. And ultimately, we want to build a systematic framework where we can deploy the security in a multi-layered security stack. And so we can have a systematic framework for evaluating and also hardening those agents against more general context manipulation attack. So that's all of my talk, and also thanks everyone. Thanks all the collaborators. Any questions?
Very interesting, especially as you're identifying, money's going to go into this market, right? Because of this stable coins, and I think the financial Wall Street is thinking about how to use agents to manage money and so forth. So your research is very timely. I'm just curious, as you're looking out forward and as agents are going to start managing more money, we've already seen some agents doing some VC investing. I'm sure they're going to do private equity investing and, stock market investing. How big do you think the danger is going to be? Like you did it relative to Eliza, whatever that is. That was a $25 million market, and you could extract how much out? I know you did it on the test net, but what's the percentage? Is it like 1 or 2%, or could you have pulled out 10%? I mean, what's that?
Potentially do all of it.
Oh, you could have pulled it all out.
Potentially, yeah.
Oh, wow. So that's a very interesting. So when you attacked, there's no defense, basically, right now.
Yeah, for the current system, right? And so this is like, I think they, like Eliza OS, they're building a framework, so they want lie those responsibility to like the users, the developers, to control the security. And for example, if you want to trust the agent to manage your wallet.
You know what you should have done is just attack them, take all their money out, and say, oh, I'm sorry, here, we'll give it back. It was just research. You should watch out for that vulnerability, right?
Yeah.
That's very interesting. That's interesting. Thank you. So you could have, wow, that's amazing. That's crazy.
Any more questions for Peiyao? Oh, I saw the hand before, but I'll come to you.
Great talk. Could you give more detail about the fine-tuning that showed promise?
Mm-hmm. Yeah, sure. So the fine-tuning here, we extracted the some commonly used API call, which includes like those crypto scenario and other domains. And these are just like, you just have the real answer, but then we extend it with the attack scenarios that we are like analyzing in the benchmark as well, that we use the similar way, but like construct different kinds of attack variants of these data points. And we just train it, and like if it's in an attack scenario, definitely the answer is you should not trigger the attacker's tool as expected. So this is the fine-tuning process.
Did you see any difference, like I don't know if you had a chance to test this attack closed LLMs versus open LLMs? Mm-hmm. And are you seeing a big delta that maybe we should not use a lot of open LLMs because of these vulnerabilities?
Yeah, so I think definitely like at this point, for all these models, they are still vulnerable to this kind of attack, either the standard primary injection, or if they have other architecture, it can also be further exploited. So I think at this stage, what you need to do is like, if you want to trust it for some important ability, like managing your wallet, and there should be a very strict rule that you set to the application you want to run, that if you want to do transfer, then maybe there is a limit, or if you want to whitelist. So we still need those deterministic rules at this moment to do that. And what we want to do is we want to actually get a model that is more adaptive and more like secure within its own responsibility inside the model to like get warning or get any alerting when those security vulnerability is detected. But I think so far, it's always a trade-off between the security and utility. If you want to be exact secure, then you need to specify the utility you allowed it to perform. Thanks.
Great. I think these are all the questions. Thank you, Peiyao.